Very good, very good. So hello everyone that joined us now. So we are ready for the second talk today. So we have here Erik Lewerenz and Heiko Radde. They both work for the Berlin Space Technology. They are a software engineer and security engineer, and they're gonna present us today how deploying post-quantum cryptography on newspace satellite. So thank you a lot.
Yeah, thank you a lot and for coming to this talk. So, and thanks for the great introduction. So we are Erik Lewerenz and Heiko Radde, both working at Berlin Space Technologies, BST. Erik has been working here as a security engineer, as a student, and doing his master's thesis, and continued working with us for the crypto system. And I myself have been working at BST now at around 8+ years, mainly focusing on the main onboard computer firmware, SATCOM, and related things. So a quick introduction to the company. So we are, like the name says, located in Berlin, Germany, have been around for 12+ years. Now around 50 to 60 people in Berlin, and a few others in India and the US in joint ventures. And we're building both and selling both subsystems as well as complete satellite systems. Those are by one the legacy LEOS 50 bus we have, which supports around 13-ish kilograms of payload. And there are multiple systems in orbit of that. And then we have the new LEOS 100 bus, which is currently in production and will support for up to 250 kilogram payloads. It's modularly designed. So with that out of the way, let's get going to what we've been doing in regards of getting our security up to snaps for the quantum computer threats. So first question. What's quantum? What's it good against? Oh God. So there's two main things concerning us. One is the Groover algorithm, which will be bad news for hashing and symmetrical algorithms, but it will only reduce the security level of those. So it will help with speeding up brute force attacks against them. And the second is main concern is, of course, Shor's algorithm, which completely breaks traditional asymmetric cryptography, and also those we've been using before. So why do we talk about this now when there's not much quantum computers around until now? Well, the BSI, the German Institute for Cybersecurity, is estimating that in the early 2030s we're going to have a cryptographically relevant quantum computers available, meaning quantum computers which, when executing Groover's algorithm or Shor's algorithm, will be relevant for the key sizes we are today using. And well, in our industry, right, we have development time, then we have the lifetime of the satellite, and then the second retention maybe of the data we downlinked. And all this combined is gonna be bad news for early 2030s. So if you say, well, we do have 2 years of development time plus 7 years average time of the lifetime of satellites, then we are already in the 2030s, and we haven't even talked about sequence retention. So the designs today do have to have this on board now. Otherwise, you're gonna be in bad luck later on. So what is the current state at BST? So we do both do key exchange for our for getting the keys synced between our operation center and the satellite. For that, we have been using classical Diffie-Hellman key exchange with RSI signatures. And from those, we then deduce our AES keys. We've been running AES 128, 192, or 256-bit key sizes in Galois counter mode, so box standard for COM security. So, as said before, the key exchange is gonna be completely out of the window. It's gonna be completely broken. And well, at least we're gonna have still AES, but we should get rid of the 128 or 192-bit key size options. So in the future, we're only gonna run with 256-bit key sizes of AES in Gala countermount. But we need a replacement for the various key exchanges we need to do not for in regards for comm security and others. Well, thankfully there had been this nice NIST competition going on. Many people providing possible algorithms for those, but well, it's not all smooth sailing. So we have here a nice little overview of the various algorithms which were proposed and partially already adopted during this NIST competition. First of all, we have 3 types here. We have the lattice-based, the code-based, and the hash-based algorithms, and both with various pros and cons, but most of them with atrocious key sizes, either public keys or secret keys or the ciphers or the signatures generated by them. Atrocious in regards to our nice embedded systems with, like, in the Leos 50 bus, we have like 72 megahertz processors and, I don't know, maybe 50 kilobytes of RAM, if at most. So we are gonna have bad luck with megabytes of keys. So, but there's a few things on these tables which we could also deploy on legacy systems, right? Mainly MLChem. But, so this table is both, right? We once have here signature schemes and we have cipher schemes. And we kind of want to replace a key exchange with a signature. But MLChem is a cipher scheme. Well, but there are solutions for even that.
Okay, so hello everyone. I'm going to explain to you the protocol we designed for key exchanges. It's called TripleCam, and the basic idea is that we replace the post-quantum signatures, which are quite substantial in size, with just key exchange mechanisms, or key encapsulation mechanisms is what they are called. So here, there's a lot going on this diagram. I just want to point out 2, maybe 3 things. First of all, we have implicit authentication instead of using signatures for authentication because they are much more efficient, because they are smaller. And for that, we have actually 3 key exchanges in one. We retain static keys for both the satellite and for the ground. And then we generate a session key on the fly for each key exchange. And then in the end, we combine them using a key derivation function. And more on that later. Also see that we only have to send one message from the ground up to the satellite, and then we return one message from the satellite back to the ground. Okay, so then MLChem and HQC, 2 key exchange mechanisms that will be interesting for us. First of all, HQC, it's called Hamming Quasi-Cyclic Chem, a very nice word. It's not really important to understand now what exactly is happening there, but it's a code-based algorithm, which means it's based on error-correcting codes, and you can actually also use error-correcting codes for cryptography, which is quite nice, and they did that, and it's very smart. And this algorithm was selected by the National Institute for Standards and Technology, so in the United States, for standardization, actually this year in March, and we're going to use that one. The other one, MLChem, old favorite, it's lattice-based cryptography. It has already been standardized by NIST, and we're also using that one. So why is that nice? They have completely different underlying mathematics, so if one is broken, well, the other one probably isn't good for us. Still, do we trust post-quantum cryptography? Not really, no. Not really, not yet entirely. So what is our plan? We're combining elliptic curve cryptography, which we do kind of trust, unless there is a quantum computer, which there probably isn't. And we combine that with post-quantum cryptography, and what we get is X-Wing. That was figured out by a lot of smart researchers. This is what it looks like. You actually don't just append the different cryptographic buffers to each other. It's a bit more involved. But what is really nice about that one is that if one of them is broken, the other one retains its full security. If you don't become a bit fancy about combining the two methods, you actually risk that if one is broken, the other one is also broken, even though you don't have a quantum computer. So just a thing to keep in mind. But with this X-Wing, this was proven that this is secure. It's good. Okay, so BST tailored TripleCam, we had to do a bit more to make this work. Can we just combine the 3 shared secrets? So the 2 static shared secrets and the one that we generate on the fly in the session, like this? Nope. This one is no longer IND-CCA secure, which is a security standard that is required of a single cam. And now if we do this, so we just hash the 3 shared secrets together and then hope for the best, we are actually less secure than a single cam. So good job, us. Another problem with the TripleCam protocol itself, we actually don't really have mutual authentication if we do it like this. So it's never easy. What can we do? This. So we build an AES chain and encrypt the shared secrets with each other. This one helps us retain the IND-CCA security. And then what we also do is we bind our public keys of the cams, or the encapsulation keys if you want to be a bit more modern about the naming. And we also put them back into the key derivation function. And then we also have the mutual authentication back. This is not necessary for all different types of post-quantum cryptographic algorithms, but I don't want to go ahead and analyze all of them, so I just add the public keys in my hashing and be done with it. So this is what we end up with. This is a very high-level overview of the VST implementation of TripleCam that we came up with. So again, you see there are 2 messages that we send. We call one the initial contact, and we call the other one the satellite reply. Very imaginative. And on the ground, it's not that interesting to look at this. So we just look at the satellite, and you can see this is basically an overview of the satellite firmware. We have 2 areas. We have the stable part and the volatile part. And we have protected areas, and we have not so protected areas, I would say. In the stable part, you can see on the satellite there is the encapsulation or the static key of the ground station, and we have the seed of the satellite key, because storing the entire key, which is about 3 kilobytes, is not very efficient. So we just store the seed and from there derive the key on the fly as we need it. And then in the volatile part, you see at first all of the cryptographic buffers that play a role in one key exchange, and of course at the very bottom in the protected area, our derived shared secret key. Nice. So what did we do? We actually did a little testing of this. There is this nice satellite that BST can use. It's not our satellite, but we have a right to use it. It's the AFR satellite. It's a small satellite, about 80 kilograms. And yeah, we uploaded the firmware to this satellite, and then we did some testing also, and we did the TripleCam protocol that I just showed you in the slide before with MLCam 3 times combined with X-Wing and elliptic curve cryptography. And yeah, we did a key exchange. So we uploaded the 2,396 bytes. Yeah, I remember that correctly. And then we downloaded the 2,360 bytes over UHF. And yeah, that's what we came up with. We get a correct key on both sides, so we did a successful key exchange. Why is that so nice? The computation time of the entire TripleCam protocol on the onboard computer was less than 300 milliseconds, not microseconds, that would be too nice. So less than 300 milliseconds, which is less than the round-trip time for communication. So now we're in a regime where we can just have session keys instead of just doing a key exchange every once in a while. I think this is actually a much bigger deal to have session keys than to just have post-quantum cryptography, because now whenever we log on the satellite, we get a new key. That means forward security is actually a thing that we actually now have. Okay, so as already said, session keys, very nice. And another thing that allows that we now have, since we have a very efficient key exchange mechanism, is that we can also have different access levels of commands for different areas of the satellite. So you could imagine that if I want to write to the memory of the satellite, that is a quite an intrusive command, whereas just commanding the payload of the satellite is probably not as intrusive. So you would want to distinguish between these two. And now we can actually do that. Another thing, buzzword, crypto agility, we can actually exchange the post-quantum cryptographic algorithms and for each other. So we both have HQC and MLChem integrated into the firmware, and even after the launch, if we figure out, oops, one is broken, well, you just tell the satellite, use the other one, and we're good. And the last thing, formal verification. So the TripleChem protocol, the plain one I showed you at the very beginning, we and other researchers had this run through formal verification program. It's called Tamarin. And some problems appeared, especially with the mutual authentication. That's what was discovered there. And that's how we came up with the design as I showed it to you, because there was some things. And now actually the final design that is formally verified using the protocol, and you can take it as it is, and you can trust it as you please or not please. Okay. It's always good sport to quote who we took our work from. So the original TripleChem algorithm is actually taken from the Kyber paper, so the researchers that came up with MLChem. We used the X-wing construction from this very beautiful paper. It was written by Barbosa and a lot of his friends. And the entire post-quantum cryptography that we use is taken from the open source library liboqs. They actually have very beautiful, formally verified implementations of MLChem at the moment integrated into their library. And I expect for HQC they will do the same. The current implementation of HQC is a bit questionable, but yeah. I think once HQC is standardized next year, we will also have a very good implementation of this one. Okay. So that's it from my part.
Thank you a lot. Thank you. Yep. It's complete. Okay. Thank you, Heiko and Erik. So, do we have questions? Otherwise, I can start with one. Meanwhile, you think about your questions. Yeah, you mentioned about MLChem. Something that comes with this kind of algorithm is that they have also requirements on the hardware. MLChem requires a good random number generator to generate ephemeral keys. So normally on the ground, we have quite a lot of freedom to deploy our infrastructure, but satellites sometimes they don't, I don't know, I don't want to say that they don't have good hardware, but it's different hardware. So it means that this kind of approach will also change hardware requirements for satellite in the future.
Yeah, definitely. So, but BST being a newspace company, we do use quite a lot commercial off-the-shelf components. So we actually do have microcontrollers deployed, which do have in hardware random number generators, and we then combine this. Additionally, we use it as a seed and use what's called again?
Yeah, so we use so we basically modeled our random number generator after the one you can find in the Linux operating system, and we use the true random number generation from the hardware we have, and then also we use telemetry data and all kinds of sensor data that is on the satellite, and basically have a entropy pool that we update every once in a while, and then we use a what was it called, the extended output function Keccak based construction. So it's SHA-3, and we have an entropy pool that is managed via this. So it's I would say it's reasonable, and it's basically the same kind of security as you would have on the ground.
Thank you. Do we have other questions? Okay, maybe I have a second question then. About you showed how to combine post-quantum algorithm with ECC, that is a good algorithm today, but will be broken in the future. to me, it seems that requires a lot of computation. And here, so in sense, you have to be able to deploy on the satellites several tools to run one and the second and third algorithm and so on. You showed about you showed key size is quite a change in post-quantum. Is also the software size that is gonna change, or the algorithm are still
well.
Small.
Different to maybe classical cryptography, we don't have in hardware implementation of them yet, so no hardware acceleration. So of course we have to have all in software, so we do have an increase in code size there. But we were able to fit it, at least when only using MLChem, also on our legacy platform, right? And on our most current platform, we go from like 72 megahertz to 800 megahertz, and also radically increase in RAM size. There we can also use then a few others as well. But even on our really low spec 72 megahertz ARM processor, we were able to deploy these, and maybe we don't get 300 milliseconds on that one, but maybe a second on that one, but even that is natural, because also the traditional cryptography on that would have also been in software and would have been way longer.
Thank you. Yes.
So I have two small questions. You mentioned Tamarine. So in Lowe's hierarchy of authentication, did you achieve injective agreement with your algorithm?
Yes, actually, we did that.
Very good. And you mentioned Tamarine, and did you also use cryptography to actually verify the implementation of the authentication chain?
Nope, we only used, so it was only in Tamarine to verify the protocol layer, and personally I thought it was not really necessary to do this with the cryptverif, because we are using the formally verified version of MLChem native. It's quite new, and this one is actually verified. So.
All right, thank you.
Oh, thank you for that. There's been presentations here about quantum key distribution and use of entanglement, and it's obviously a very new concept that they're looking at, and they're looking to trial that. Is that something that you guys would consider going forward, or do you have any views on that compared to the work that you're doing on this?
Well, we haven't explored it too much, mainly because of the hardware availability problem and the distribution problem, right? The very nice thing is we are, with this, very hardware independent. We can deploy it on today's hardware, and are currently not strained by any special hardware being also present in a grounds operation center. We could move to different grounds operation centers, etc. So for now, right, these problems persist with quantum key distribution. I guess we'll stick with that. But of course, if those are solved, then quantum key distribution is very fancy and interesting thing to also add to the system. But for now, this is kind of the best we can reasonably deploy on our satellites.
Good morning. Thank you very much for your presentation. I have also a question about how long does it take to negotiate a key between the ground and the satellite, just in terms of satellite visibility for low Earth orbit. Do we need several periods of visibility, or does it suit in only one?
No, so the computational time on set is 300 milliseconds on our current platform. So we need 2 messages of 2 to 3 kilobytes to be transmitted. So this is over S-band doable within like 2 or 3 seconds.
Sorry?
2 or 3 seconds via S-band.
Okay.
So really depends on your com setup, of course, how fast you upload 2 to 3 kilobytes, but.
Okay, do we have a last questions? If it's not the case, thank you a lot one more time, and
thanks for having us.